Good morning. I'm David Green and I'm your teacher for this semester. I would like to start this morning by providing you with a little introduction as who I am and what it is that I'm doing here. I have spent the last 10 years teaching at the college level. I am presently a full-time teacher over at Bryant Stratton College. I teach a mix of networking and security classes. So now that you know a little bit about who I am, let me tell you a little bit about what my philosophy of education is. I believe that education provides the pathway to fulfillment in the life of an individual. Education allows for individuals, you, me, to be able to find that thing that makes us really, really happy about our lives, whether it's a job or it is a hobby that we've gone to school for. It doesn't always have to be that our education centers strictly on those things that will get us a position in the world of work and will get us gainful employment. Many times we might decide that we want to seek out educational opportunities so that we can increase our knowledge of something that might be a hobby that we choose to follow, or it might be something that we seek out for personal fulfillment. So education provides a large kind of avenue for us to be able to seek out and find those things that really make our lives fulfilling. Now, if that's the purpose of education, in my own opinion, what is it that a teacher does? What role does a teacher play in that? Well, a teacher's job is to build the bridge. Build the bridge? Not a physical bridge necessarily, unless I am teaching a course in engineering and architecture. But probably the bridge we're speaking about in most circumstances is building that bridge between what you know and what you don't know. Now, that may sound like it makes perfect sense, but how do we get there? Well, it's actually a process that we have to go through. We go from a known concept that has a known process, and we move to an unknown concept and an unknown process. So we start this process going from what we know, and in some way we find out through education that we can acquire concepts and ideas, knowledge, learning about concepts that at one point in time were unknown to us and had unknown processes. So that is our quest, if you will. That is what, in my opinion, education and the role of a teacher really truly is for us. Now, in order to accomplish this, an educator like myself has to have certain skill sets. There are really two essential skill sets that separate really good teachers from other people who either are pursuing other lines of business, and I spent over 20 years in the business world, and I've seen skill sets possessed by people in the business world that make them very successful. But as a teacher and as an educator, there are two essential skill sets that we need to have. First off, we do need to be subject matter experts. We do need to know the material that we're talking about. Now, beyond knowing our material, in the case of networking and information technology, it might be understanding things like how it is that standards and protocols of networks help information to get from point A to point B. Any type of really subject matter that's necessary to be able to have information to convey to students is essential. Secondly, and probably in most instances, this is what makes a successful teacher, you must be practiced at the art of explanation. This gets back to what we were talking about as far as building that bridge from the known known to the unknown unknown. Well, how do we go about doing that? Well, there are a lot of tools in a teacher's tool bag that can help them to try to get from the known known to the unknown unknown. First off, one that I rely on quite heavily is relational learning. That's taking what you do know and relating it in some way to what you don't know. Oftentimes, this is wrapped inside of an analogy. An analogy can be very, very useful because it, in essence, is taking what you know how to do and moving to what you don't know how to do. Now, in trying to find out how we can try to make that happen, oftentimes we aren't successful as teachers. Oftentimes we might try a certain approach and utilizing relational learning to have students try to understand a concept. That may not work. So what it requires also as a teacher is that part of being practiced at the art of explanation is that as a teacher, you're not tied to only doing things one way. I know that in the process of my past teaching experience, I often would run into situations where students didn't quite grasp what was kind of trying to be understood. So some students might get it, but other students not so much. So it requires this thing called dogged persistence and the ability to be flexible as a teacher to try different methodologies. And if for some reason a student doesn't quite grasp a concept or an idea or a learning objective, you have to find other ways. So that's what my job is. And it really does set into my entire philosophy of the purpose of education and my philosophy and approach of being a teacher. That's what I have kind of honed as a skill set for the last 10 years as a post-secondary educational professional. So, now that you understand a little bit about me and my philosophy of education, let's get on to what today's topic is. And that is a review of the material that was covered in one of your prior courses. In your Fundamentals of Networking, one of the subject areas that you explored was IP addressing and more specifically subnetting. How is it that we go about taking a large network and break it into smaller pieces? So today we'll talk about how we go about the process of creating subnets, or as I like to call it, having fun with ones and zeros. So, topics that we'll talk about today within the context of subnetting. First off, we'll talk about IP address classes. We'll talk about default subnet masks associated with those IP address classes. Then we'll ask the question, why do we create subnets? And then we'll look at some special IP addresses in each network that we can't assign to hosts within that network. And then finally, we'll do some network design, looking at some examples using subnets and how we go about creating those smaller networks within the larger network so that we can efficiently use our network IP address space. So, first off, address classes. Classes of IP address. We learned last semester, or in a prior semester, depending upon when you took networking fundamentals, that we break our address classes for IP addresses into 3 useful, 5 total IP address ranges. And we determine what class an IP address is based upon the very first octet of that IP address. If the first octet of the IP address is between the number 1 and 126, we say that is a Class A IP address. If it's between 128 and 191, we say it's a Class B. And if it's between 192 and 223, we say that is a Class C IP address. Now, there are 2 other classes. They are not classes that are actually utilized on the public or private networks. Those are Class D and Class E. Those are traditionally reserved for either research, quote unquote, or also for protocols, such as certain specific routing protocols might use an address, say 224.0.0.9, utilized in certain routing protocols to convey information. But we do need to remember in doing this that what we're really creating when we look at creating an IP address network range is we're really talking about a logical address scheme. It's not something that is physically burnt into any specific part of a device on the network. We'll leave that to the MAC addresses. And we must remember that 127 as a network first octet value is reserved for loopback. That allows us to be able to check whether or not the suitable protocols are active within our individual device. And the more specific IP address used for that is 127.0.0.1. All right, now let's look at what those classes look like associated with their default subnet masks. We'll look at those both in dot decimal as well as in binary. So, associated with the Class A IP address range, we will have a subnet mask that has a 255 in the very first octet, with the remaining 3 octets being reserved for hosts within that class of IP. A Class B, we find a 255 in both the first and the second octet, while the last 2 octets are reserved for host addressing. And in a Class C, we see that we have 3 octets that are populated with 255, while the 4th octet is reserved for the host portion of the IP address range. Binarily, you'll see that 8 ones occupy that first octet in a Class A. The 8 ones have a value when added together of 255. And subsequently, 2 octets binarily are filled with 1s in a Class B, and 3 octets are filled with 1s in a Class C. You'll notice that the host portions are filled with 0s in each of those individual classes when it comes to the binary equivalence of the dot decimal. So, the class determines which part of the address belongs to the network and which part of the address belongs to the host. So we can look at a Class A and say, those first 8 bits, those are all network bits. And you'll see that those are represented there with N's. And you'll see the host portion, they're listed there as with H's. So in this way we can kind of see what portion is network and which portion is host. Instead of looking at 1s and 0s, we can see that when we have a Class A, the very first octet will be network, the first 2 in a Class B, and the first 3 octets in a Class C are the network portion, with the last octet in a Class C, the last 2 in a Class B, and the last 3 in a Class A reserved for host assignment. So, why do we go about creating subnets if we have this class-based IP address system? Well, what they allow us to do is they allow us to be able to organize information in some ways, meaning this information is where an individual device sits on a network. So take for an example, if we had a large Class A for an organization, like say a college. Well, that college might have several smaller buildings or organizations within the college campus. And we might decide that we want to use subnetting to be able to delineate what organization has which range of IP addresses. So we would create smaller subnets out of a much larger, say, Class A IP address to be able to create those smaller network IDs for each of those individual either buildings or organizations within the college campus. It also keeps routing tables smaller. This is very important because a router is operating with a fixed amount of memory, storage, buffer, and we don't want to clog up the routing table with routes that really we could combine or make smaller and allow the router to be able to see much more readily where it is that the packet, or if it's at the transport layer, the segment needs to go within the network. And then also, we want to use subnetting to be able to minimize the broadcast domains. Broadcast traffic on a network is it's necessary, but we don't want so much broadcast traffic that we take up a lot of space, a lot of overhead on our network. So creating subnets ensures that messages that are sent out on a network go to the smallest number of devices that are necessary for that message to have meaning and be needed by those end devices. Now, the subnet mask plays a very specific purpose in the role of IP addressing. First off, it tells the device which part of the address is the network number and which part is the host. And it probably also includes, if subnetting is taking place, which part of it is actually the subnet. Because we know, based upon class, what the defined default subnet masks are. So if we see extra bits associated with the subnet mask, we should go, aha, those must be subnet bits. So what takes place is a device will filter out the host portion of the IP address to determine which subnet or network the IP address is trying to get to. So, does that mean that we don't care about the host portion? Well, certain devices don't, like a router. A router does not pay any attention at all to the specific host portion of an IP address. A router is trying to get the packet to the end device utilizing just the network and subnet portion. And the subnet mask is like the decoder ring that tells the device, hey, this is the way you go about trying to figure out which part of this IP address you need to pay attention to. The subnet mask does that for us. We can look at network bits, subnet bits, and host bits, and then we can try to figure that out. So every single IP address is made up of those three parts: network bits, subnet bits, and host bits. And a router will only pay attention to, yep, you guessed it, the network and the subnet bits. Now, why does it do this? Well, let's consider what happens at a post office. When you drop a letter or a package off at the post office using snail mail, that letter has a zip code associated with it, and it's its destination of where it's going. Now, zip codes are traditionally 5 digits with a dash, and now today 4 digits after that. So what do all those mean? Well, they've got a protocol to follow, and the first part of that zip code is the part that the post office pays attention to first and foremost, because that will get it to the correct distribution center. At that point, the post office is not really concerned with the rest of the zip code. At that point, the post office is only really concerned with getting it to the distribution center. Once it's there, then the distribution center will pay attention to the last 2 digits in that zip code. And once it gets to that local post office and it gets to a mail carrier and it gets slotted into the mail carrier's daily trip, that's where those last 4 become necessary and useful. So just like that process, we utilize our IP address to create different parts that different devices will pay attention to. So, how do we go about trying to figure out how many subnets we can create? And I mean, what's really just the math that's going on here? Well, first off, we can calculate the number of subnets that we're going to create by the number of bits we borrow. Yeah, we're borrowing them. That doesn't mean we're going to give them back. I mean, we use the term borrowing, but really what we're talking about is we're going in and taking some of the bits that used to be associated with the host portion of the IP address, and we're swinging them over to the network portion. So we start with our default class-based IP addressing. Then we say, hey, I've got a class A, and I want to create subnets. Okay, how many subnets do you want to create? And whatever number of subnets you want to create, it's going to require you to borrow some of the bits that are presently sitting on the host side and make them network bits, subnet bits. But they're going to do the job of the network and help to define the subnets that we're going to create. The formula for that is 2 to the power of the number of bits that we're borrowing. So, what could this look like? Well, for a class A, where we have 8 bits that are dedicated network bits, we have 24 host bits that we can possibly borrow bits from. Now, if we were to borrow all of them, that's the number we would be looking at. So that's the total number of empty subnets we could create. I say that kind of just in theory because we would never create networks that didn't have any capacity to be able to have host IP addresses assigned to them. But in theory, that's kind of what the math looks like. We have 3 available octets to create our subnets with. In a class B, we have 2 octets available to us. And in a class C, we have just 1 octet available to us. Now, that's the total number of subnets that we have available to us. So what does this look like? Well, this chart that you see there, I know it may look a little daunting, but if you remember from the networking class that you had, those are actually the values of each of the bit places within an octet. So, when we look at an individual octet, we have 8 bits. The very first bit, the farthest to the right, has 2 options to it. So therefore it's a base 2. And anything to the 0 power is what? 1. That's right. So just like we have our tens, hundreds, and thousands, we also have our ones place in our traditional deca world. Here it's much the same, but we're not talking about base 10. Instead, we're talking about something that's a base 2. Only 2 options, a 1 or a 0. So depending upon where it is that a bit sits in that kind of framework will determine what the value is. And you'll notice we're only counting ones. Why? Because anything times 0 results in, yep, you got it, 0. So, as a for example, if we had 1 followed by 7 zeros, then the value for that IP address in that octet would be 128. Now, I know that when you look at this, you say, but how come I don't see places where I've got ones, I've got a few zeros, and then I go back to having ones? I can have that in an IP address, right? Certainly. However, in terms of a subnet mask, we don't have that. Why? Well, because in a subnet mask, we're looking at some number of bits that are turned on. They're number ones. And those ones indicate some number of bits that are being borrowed out of that octet to be able to create the subnet. So therefore, we're going to have the number 1 in a placeholder starting with the most significant bit. And then if we need to borrow additional bits, we'll borrow the next one over. And when we're done borrowing the bits to create the subnet numbers that we want, we're done. So we don't need to worry about jumping around between a 1 in the 128 and a 0 in the 64 and then a 1 in the 32 slot. No, we are borrowing 1 bit, 2 bits. If we're borrowing 2, we have the 128 and the 64. We call these utilizing the most significant bits, and we use them in order. From the most significant, meaning the highest value, in this case 128, and as we go down the line, depending upon the number of subnets we need to create, the value increases, as you see there on the far right-hand column. Those values, along with 0, are the only values that you will see in traditional subnet masks. You're not going to see any other values. Now, the nice thing about that is that there's what? Oh, there's 8 values I need to make sure I can recognize and know. And that's a positive. So look out for any one of those values. And when you see them, try to learn what the number of bits are that are actually being borrowed to be able to make up that number. That will help in being able to quickly determine how many subnets are being created, as well as the range of subnet IP addresses and the network and broadcast IDs for each subnet. So let's remember that there are some special addresses in each subnet. Now, an IP address of all zeros in the host portion of any network or subnet, that is the network or subnet number. That identifies the entire network. So when you see something that is, say, 192.168.1.0 with a 255.255.255.0 subnet mask, when we look at the zero portion of that, we know that that then is the network ID for that network. It defines the entire network. It's not an IP address that can be assigned to a host. Instead, it represents the network ID. Additionally, if we had all ones in that host portion of an IP address, that would be a special IP address that we also cannot give to a host. That would be the broadcast address for that network. This is important because a broadcast address is necessary in order to be able to send out a message that all the devices, hosts, on a given network will pay attention to. So it creates a very, very special broadcast that everyone is going to pay attention to. And it's recognizable because when we match the network part of the IP address with all ones in the host portion of that IP address, then we know, that is a broadcast that every single device on that network is going to pay attention to. Let's look at some examples. Let's take for an example 192.56.32.13. That's an IP address. What class is that? Now let's remember, way back to the first slide, when we had the range of IP addresses and we were trying to figure out, all right, is it a class A, a class B, a class C, D, or E? I promise, I won't throw any D's or E's here in any of these examples. 192 is, yes, it is a class C IP address. What is the default subnet mask for a class C? Do you remember? It is a 255.255.255.0. The first three octets are being utilized with a class C. And since we know 192 is a number in the first octet that reflects a class C, that is the default, meaning unsubnetted subnet mask. So, what's the network address? Well, if we remember that, that means that if we have three octets that are network in a class C and one octet that's host, and if we put all zeros in that host portion, guess what? We get 192.56.32.0. That is the network address. And that's an address that we can't assign to an individual host on the network because it's a special address. At the other end, what's the broadcast address? Well, if you remember, we take a look at the network portion and we leave that, and then we take the host portion that in terms of a network address was full with all zeros, and we change all of those to ones. Now, if we did that with the 192.56.32.0, if we took that zero and turned all those zeros in that fourth octet into ones, what number would we have? I'll do the hard part for you. It's a 192.56.32.8 ones. What's the value? It's a 255. Yes, if we took ones and put them in every single one of those bit placeholders and we added up all those values, we'd come out with 255. Now that we have that under our belt, let's take a look at a subnet mask example. Let's take a look at 192.56.32.13. We know that 192.56.32.0 is the network address. And we know that there are 8 bits available. That means for host addresses, we're going to borrow 1 bit. So we're going to go into that fourth octet where we have 8 available host bits. And we're going to borrow a bit. Which one? Right, the most significant bit. That very first bit, farthest to the left in our placeholder setup. So it's going to look something like this. 3 octets filled with network bits, 1 bit filled with our subnet bit, and then 7 remaining host bits. So, what's the subnet mask? Well, we know it's 192, we know it's 56, and we know it's 32, and then we're using 1 bit there, so our mask has got to reflect, 255, 255, 255, because we know 192, 56, and 32 are part of the network. What is that 0 going to turn into? We borrowed that most significant bit, and its value is 128. So it looks something like this. And if we put up the values of those placeholders, this is what we see. We see a 1 in that very first slot. And that means our subnet mask is 255.255.255.128. Good job. Now, let's take a look at another one. Let's look at 177.56.45.13. What class of IP address is this? Right, this is not a class C. This is a class B. Does that make things completely different? No, not at all. We follow the exact same process we did for our class C, only we're utilizing a different octet here to be able to create our subnets. Because here, our default subnet mask is not 255.255.255.0, but instead 255.255.0.0. Because in a 177, which is a class B, only the first 2 octets are network octets. The last 2 octets are host octets. And we're going to borrow 2 bits this time from the subnet mask to create our subnets. Let's see what that looks like. It's going to look like this: 16 network bits, 2 subnet bits, and then the remaining 14 bits are going to be our host bits. So what's the mask? Let's see. It's 255, 255. What happens to that third octet? We know the fourth stays as a 0. Why? It's all still host. But that third octet has 2 bits that have now been borrowed from the host side and moved to the network side. So we know the most significant bit was 128. What's that next slot? 64. So what is 128 and 64 added together? 192. Exactly. So that means our mask is now 255.255.192.0. Let's take a look at a subnetting example and determine how many subnets we can create. We'll utilize an IP address of 196.54.32.22 as an IP address sitting presently within the network. We're going to borrow 2 bits to create subnets. So as you remember, the number of subnets that we're creating is 2 to the power of the number of bits borrowed. So 2 to the second power, we're borrowing 2 bits, 4 subnets. So we're going to create 4 separate subnets out of this. What are the number of hosts that we can put on each of these subnets? We've got a formula for that too, if you remember. That formula is 2 to the number of host bits remaining, and then we have to subtract out, not from the exponential number we're using, but after we've done 2 to whatever power, we subtract 2 from the result to be able to account for the network bit, or the network IP, and the broadcast IP. So in this case here, since we're talking about a class C, and we borrowed 2 bits, we have 6 bits left over for our hosts. So 2 to the 6 minus 2 leaves us 62 available IP addresses that we can assign to individual hosts on the network. So as you can see, we subtract 2 because the number has to account for both our network bit and our host bit. Let's look at another example. We're going to borrow 2 bits from 196.54.32.22, and that gives us 62 hosts and 4 subnets. It looks something like this. Let's look at that last octet. It looks like shh, but it's really subnet, subnet, host, 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 host. So We count to 4 in binary using 2 bits, and all those combinations of ones and zeros become our new subnet IDs. What does that look like? Well, the first subnet, we use our 00. That's the first combination we can make, right? So our first subnet address is 196.54.34.22. Excuse me, 196.54.34.0. That's our subnet address. And the IP address range would be one more than the subnet address, and then up to where we would have our broadcast address. But in order to find our second subnet, we're going to take a look at our 0-1 combination, and that's going to give us our second subnet. Now you'll notice that we're dealing with the 0 and 0 in the most important bit section of our octet. So the first and the second bits, which we know are valued at 128 and 64. So our first combination is 0, the second combination is 0-1, which means that a 0 in the 128 slot, but a 1 in the 64 slot, for a value of 64. That's our second subnet address. Third combination we can make out of those 2 bits, a 1 and a 0. That makes our third subnet 196.54.34.128 for our subnet address. And then last but not least, our fourth combination with those 2 bits is a 1-1. And that gives us a network subnet address of 196.54.34.192. And those are the 4 subnet network addresses that we can create out of the Class C 196.54.34.0, where we change the subnet mask from the traditional 255.255.255.0 to 255.255.255.192. So let's wrap up and take a look at what it is we've learned today. First off, we talked about IP addresses being a logical construct. And then we looked at 3 broad classes of IP addresses that we utilize for public and private use. Those are A, B, and C. D and E, we mentioned, are used in research and for protocols to be able to send information. The subnet mask is used to define the network and the subnet part of the address. It lets us kind of have a decoder ring to be able to see what part of the network is network IP and what part of the IP address is subnet or is host. We can use subnets to design networks by dividing large networks into smaller networks. This allows us to make more efficient use of our address space. And that really is predominantly the reason why we want to do this. We want to be able to more efficiently utilize the IP address ranges that we have, and usually by creating subnets, it allows us to be able to use an analogy, not have to eat an entire pie. Instead, we only need to take a slice. We'll talk more later on our next lesson, and remember the assignments for next week. Thank you very much and have a great day.